I think this is a very interesting question, so let's see what it's asking us. We're going to find the radius and the height of a cylindrical soda can with a volume of 412 centimeters cubed that minimize the surface area. So we're trying to sell, or rather store, the fixed amount of soda with the least surface area spent possible. So let's model the situation first. Your can is going to have a radius and a height, and the volume of your can will be area of the base times height. So the base is a circle, which has area pi r squared, times height. So that's the volume of your can. Second, you want to minimize the surface area. So when you write the area, we call it S of x. I think that's a good name for it. That will be, if you unfold the soda can, the side becomes this rectangle there, and you have the top and the bottom circles. That's how the unfolded soda can looks like. So really you have two areas of the base, so it's 2 times pi r squared plus, so this that I wrote so far are these two circles, so the top and the bottom. And now the side, right, is this rectangle here. It comes from the this unfolded side of the soda can. And the height of this is h. And the length will be the circumference of the circle. I'll even change colors here so you could see. The length here, right, that's the same as this. Just imagine it unfolding and you'll understand. So this is the circumference of the circle, which is 2 pi r. So the other area I need to add is 2 pi r h. The only problem, maybe I'll send this over that way. The only problem I have is that I need, first of all, this is S of x. I want to make it S of r instead. So that means I don't want to have h in here. So how do I get rid of this h? I used the volume. I was told that the volume is 412. So that means 412 is pi r squared h. If I want, I can say h equals 412 over pi r squared. So I could replace that there to get that S of r is 2 pi r squared plus 2 pi r 412 over pi r squared. Cancel what can be canceled. This is a pi, right? Not a 4. So I get to cancel the pi's as well. And double the 412s. So S of r will be 2 pi r squared plus 824 over r. So that's my function. So what I do next is I want to minimize this. So I want to find the derivative of that, make that equal 0, and find the value of r that makes that equal 0. So that will be this prime of r, that will be 2 times 2. So power rule on r, 4 pi r plus, and this is an r to the minus 1, right? If you rewrite this, instead of dividing by r, I could write it as r to the minus 1. So that would be minus power rule again, the minus comes down, so minus 824 r to the minus 2. So when I make that equal 0, I'm doing 4 pi r equal to 824 r to the minus 2, which is the same as dividing by r squared. So I'm making this change seamlessly. Multiply the r. 824 is 4 pi r cubed. So r is going to be the cube root of 824 over 4 pi, excuse me. So bring out my calculator to do the math. So this will be cube root of 824 divided by 4 pi. So that's approximately a 4.03. I see that my answers here are all at 1 decimal place. So that would be approximately 4 centimeters, which is not what B is giving us. So B is telling us that real soda cans have this volume, have this radius, and this height, which is totally different. So B then also goes to say that we're going to conclude that the real soda can do not have an optimal design. But that's not true, because in reality, the top and the bottom of the soda can have to be more resistant, have to be thicker. So the actual cost is not just minimizing surface area, but minimizing the cost of material. You spend twice as much material on the top and at the bottom than you spend on the sides. And if you think about it, most of the weight is on the top or at the bottom, depending on whether your box is upside down, but the box is never going to lay on its side for transport at least. So what we'll do is write a new function that's exactly the same, and instead of using surface area now, I'll use C for cost, because we're talking about material now, and we're going to double this, because this was, in the previous problem, adding the two circles, but now each of the circles counts as 2, because we're doubling the area. So this is 4 pi r squared plus 2 pi RH, and then the rest is exactly the same. So that's 4 pi r squared plus 824 r to the negative 1. So C prime will be the exact same thing we did here, right, except that now I have 8 pi r instead, minus 824 r minus 2. And when I make that equal 0, I'm actually solving an equation where instead of this 4 pi, I have an 8 pi. So r, in the same way, pretty much the same way, this will be, instead of 4 pi, this will be an 8 pi. So this will be a cube root of 824 over 8 pi. And then if I bring up my calculator again, I can just go back and replace my 4 pi by an 8 pi. And then I'll get about a 3.2, which will then be a lot closer to the value they give me of 3.1. So these are now a lot closer to real dimensions of a soda can.